Okay, next talk in our sequence this afternoon is Mat Langford, who will give us a classification of convex, ancient, free boundary, curve shortening flows in the disk. It's disk spelled with a C, unfortunately. Anyway, take it away, Matt.
Thanks, Glen. So I think either K or C are acceptable. The original word is Greek, spelled with a kappa, but it came into English via Latin with a C, so I went with that. That was my thinking on disk anyway. I'll probably change my mind in the future. So my title is basically my abstract. In fact, it's slightly longer than my abstract because of the way classification is conjugated. So it basically says it all. And I think this is I think of this kind of a nice sort of toy problem, which hopefully might initiate a bit more activity in ancient solutions and free boundary flows. So we already saw a glimpse of curve shortening flow in an earlier talk today, Noah's talk. And just to recap, the curve shortening flow is the gradient flow of the length functional for regular curves. So whenever you have a notion of sort of regular curve and length functional, curve shortening flow makes sense. And in the sort of classical interpretation is that it moves your curve in the direction, well, with the velocity equal to its curvature vector at each point. So I'm not going to really do many formulae in this talk. I'm not even going to give that one, but it's pretty easy to understand. At each point of the curve, you move it in with velocity equal to its curvature vector. This is so suitably interpreted. This is a parabolic equation, and it inherits all of the magical stuff associated with parabolic equations. And it's sort of the best of all worlds for geometric flows. And that's illustrated really well by this famous theorem of Gage, Hamilton, and Grayson, which guarantees that just about any closed embedded curve, I say just about because you need an iota of regularity, but just about any closed embedded curve can be flowed by curve shortening. It'll immediately become smooth. It'll sort of sort itself out and eventually contract smoothly to a point, and its asymptotic shape is circular. So this is sort of the best of all, of all possible worlds theorem for geometric flows. The natural Neumann condition associated with the flow is the so-called free boundary condition. So this theorem above is for closed curves. So this is kind of the no boundary condition, which is the most common thing to consider in geometric flows. And you can also look at certain boundary conditions. The natural Neumann condition is a free boundary condition, whereby the boundary of your curve, so in this case, you'll have a segment with two endpoints. Those endpoints lie on some fixed barrier curve. They're allowed to move within the barrier, but the two curves have to meet orthogonally. So the endpoints have to meet the barrier orthogonally. So there's a picture here that I stole from Ben Lambert's website. So you can see this curve is inside this convex set and meets the boundary orthogonally. So several people have sort of developed the free boundary version of curve shortening flow, mostly focused on the sort of higher dimensional setting. So Axel Stahl was one of the early people who worked on this, and he proved that convex curves, so if you have a convex curve with free boundary on a convex barrier, it'll actually flow until it contracts to a point on the barrier. So in the free boundary setting, you have a sort of version of the Gage-Hamilton part of the above theorem, and we'll use that later. Okay, ancient solutions. What's an ancient solution? Those are very special solutions to, well, parabolic equations more generally, but in particular geometric flows. They're called ancient because they're defined for all negative times. And this makes them quite special because diffusion has acted for a very long time. We expect them to be very rigid. Think Liouville theorems. Think Bernstein's theorem for minimal surfaces. Understanding them is crucial to understanding singularities. Basically, when you model singularity formation in these flows, you sort of zoom in and you take a limit, and sort of standard kind of blow up procedure in geometric analysis. What you get is an ancient solution. If you're looking at curves in the plane, these four movies give us examples of ancient solutions. So trivial one on the right here is the stationary line, has no curvature, so it doesn't move. Shrinking circle, it's very easy to figure out exactly what that should be. So you have a family of shrinking circles, which comes from infinity and shrinks down to a point. You have this thing on the top left called the Grim Reaper curve, which just translates to the right. And then if you sort of glue two of these together in opposite directions, you have what, at time minus infinity, you have what Ungenant calls the jousting Grim Reapers, and what everybody else decided to name after him. So there's these four examples, and it turns out that they're the only examples within the class of convex solutions. So in fact, there's one more. But if you look at solutions whose time slices bound convex bodies, you get these four, or you get sort of two parallel straight lines bounding a strip region. Those are the only examples you get amongst convex solutions to the curve shortening following the plane, ancient solutions. And I'd be remiss if I didn't mention the prior work of Daskalopoulos, Hamilton, and Shesham in the compact case, and Shujia Wang in a very important paper also showed that the shrinking circle is the only one that sort of sweeps out the whole plane. Anyway, that's a separate result, but basically you have this very simple classification for ancient solutions to curve shortening flow in the plane. Each of these examples is given by an explicit formula, which is quite nice. So you can see the formula here. One of them, which will come up later, is this formula for the Ungenant oval. So the Ungenant oval is exactly the set of, so at each time t, the corresponding curve is a set of points x and y satisfying this equation, set of coordinates. So that makes this problem a bit easier, I guess. If you know exactly what these candidate solutions look like, it's easier to classify. But what I want to talk about today is the free boundary setting. So I want to, we initially were just looking at what's known for ancient solutions in free boundary mean curvature flow. Turns out not very much. So we started with probably the simplest non-trivial case, as we looked at free boundary curves, which lie in the two disk and meet the boundary, meet the one circle, the circle orthogonally. This joint work with Theodore Bonney, I should have mentioned already. And we're able to get a very, very simple classification of these ancient solutions. So there's exactly one. Looks a bit like this picture here. As t goes to minus infinity, it sort of converges down onto this stationary bisector. And as t goes to 0, it collapses up to the y-axis, the 0.01. We also have this asymptotic sort of expansion as t goes to minus infinity. So you sort of have a very precise growth rate for the height over the limit bisector as t goes to minus infinity. So I'll hopefully be able to discuss, give you more or less the whole proof of this in this talk, hopefully. Also, yeah, this is sort of a toy model result. Basically, to our knowledge, we don't know of any other results for ancient solutions to geometric flows under a non-trivial boundary condition. So yeah, we're looking at the higher dimensional case. I think there's a lot of interesting things to think about there. But I think this is a nice place to start. Okay. So let me mention a couple of things first. So this classification applies to strictly convex. So this is the unique strictly convex solution. If we relax that to weakly convex, then very simple argument shows you that the only additional things you get are the stationary bisectors of the circle, of the disk. Also, you might think, okay, you look at this problem, free boundary curve shortening flow in the disk, you quickly notice that the problem is invariant under rotations about the origin. So then you might expect to find, a soliton solution which evolves only by rotating about the origin. A fairly straightforward ODE argument shows you that none can exist. So there are no soliton solutions to this problem. So that's sort of the first place you might want to look for solutions. Another remark. So the problem turns out to be sort of, analogous to classification of ancient solutions on the sphere, convex ancient solutions, which was done by Brian and Louis. But it's also somewhat analogous to the classification of ancient solutions in strip regions in the plane, which was slightly unexpected when we started looking at this. This you can presumably extend the classification unchanged as long as you include the stationary bisectors. If you relax convexity and replace that by bounded length, and there's probably additional solutions which have unbounded length as t goes to minus infinity. So consider those 2 points conjectures. We haven't thought too much about it, but that's our suspicion, that you can extend the result in those ways. Okay. So the first step is to actually produce a solution. And the first thing you realize is that the sort of obvious thing doesn't work. You make some symmetry assumption, as for, say, the shrinking circle in the plane. It's rotationally symmetric, reduces the problem to an ODE with respect to t, and then you just solve it, and then you've got yourself an ancient solution at the very least, but this doesn't work. So these solutions are definitely not, in fact, they're very far from being circular arcs, due to this asymptotics. Okay, so circular arcs definitely don't work. The soliton solutions which rotate about the origin don't work. So instead, we have to produce our solution as a non-explicit solution by taking a limit of what Ungenant calls old but not ancient solutions. Sort of classic way of producing non-compact solutions to PDE. So how do we do that? Well, we take some initial data. We take gamma rho to be some convex, locally uniformly, so positive curvature curve in the disk, which meets the boundary orthogonally at the point, at this prescribed boundary point. We assume that it's reflection symmetric about the y-axis, so that prescribes the other boundary point. It won't be completely clear in this talk. I probably won't talk too much about this, but we also produce this curve such that the curvature is maximized at the boundary, minimized at the y-axis, and monotone in between, strictly monotone in between. This makes some of the analysis easier. And the solution we construct will have this property. Okay, so we just need these properties, and let me just give the picture. So we prescribe this boundary point. We take something that's reflection symmetric, convex, and has this curvature monotonicity property. And it's pretty clear that such things exist, but to give a very explicit example of such a curve, you can take these. It's very easy to see that you can cook up this scaled time slice of a suitable time slice of a suitably scaled Ungenant oval solution. And the scale factor and the t at which these conditions are satisfied is uniquely determined. And this curve satisfies this monotonicity. Any old curve satisfying these properties will do for the construction, but it turns out that this one is a good choice to make for the uniqueness, because we can get some control over the particular solution we do construct if we use these initial conditions. Okay. So hopefully that'll come out in the wash. So okay, what do? We take our curves, and as you can see, as rho goes to 0, these curves are getting much closer to the limit bisector. So their initial speed is very, very slow. So we expect them, or we at least hope that they will exist for longer and longer times. And then in the limit, we get something that has an infinite time of existence before it shrinks to a point. And that's exactly what happens. So the lemma is that, well, we flow these things by free boundary curve shortening flow. We get a solution to the flow. We time translate that solution so that the final time is time 0 and the initial time is negative. And we get something which is, convex and locally uniformly convex, and also reflection symmetric, unsurprising. They collapse to, by Stahl's theorem, collapse to this point due to the reflection symmetry, it has to be this point as t goes to the final time, which we've made 0. You can preserve this condition, this monotonicity condition on the curvature. And you also get that these things exist for longer and longer times as rho goes to 0. So those are the properties you want of your old but not ancient solutions. And the proof I've already mentioned basically just applies Stahl's existence theorem to these initial data. Time translates, so the final time is time 0. That gives you the first 2 points, basically. The third point comes from an application of Sturm's lemma on the zeros of solutions to parabolic PDE in one space variable. It sort of tells you that if your curvature only has one critical point initially, it can't develop new critical points, and it can't lose a critical point either by the reflection symmetry. And in order to get this final point, we actually construct barriers which prevent the solution from contracting too quickly. And it turns out you can use free boundary sort of circular arcs. You can foliate the upper half disk by circular arcs which meet orthogonally, and you can parameterize them in such a way that they become a super solution to the flow. And this is the time of existence of those guys. Well, actually not quite, because you have to sit them, you have to move them up a little bit to lie above the initial data. But basically you get this nice, well, this number doesn't matter. The point is that the existent time, the initial time is going to minus infinity. Okay, so now we're done, right? We just take rho to 0. Sort of general nonsense gives us a limit. So we get an ancient solution, but there's a problem. That ancient solution could just be something trivial, like the limit bisector or something like that. So with just a little bit more work, again, using suitable circular barriers and these properties that in the lemma, we can actually show that the limit is non-trivial. It is convex and locally uniformly convex, reflection symmetry collapses this point as t goes to 0, it converges to the bisector as t goes to minus infinity, etc. So this gives you existence of a non-trivial example. Not too much effort, not too much sweat to get that. I finish at 4:55, is that right? Okay, should be enough time. Okay, so that's the existence. And let us note that, well, if we go back to how we cooked up this initial data, so if we do, use this initial data, then if you sort of look at how this scale factor lambda rho depends on rho, you can show that lambda rho converges to this solution as rho goes to 0. This turns out to be this is a useful property which makes this a good choice of initial data. We'll see why in a second. Okay. Let's see. We'll sort of see why in a second. I won't be able to give all the details, but okay, so that's the existence of some example. Next, we want to show that there are no other examples. So let's just fix some, convex, locally uniformly convex example. And the first thing we want to show is that as t goes to minus infinity, you converge smoothly to, a stationary solution. And that's not too hard to show. Okay, so the first thing that, you use Stahl's theorem to show that at time 0, assuming this is the maximum time, it has to contract to a point on the boundary. And then you just integrate the first variation of area. So the variation of the enclosed area is the integral of the speed. The speed in this case is over the boundary. Speed in this case is the curvature. Integral of the curvature is actually just the total turning angle by the theorem of turning tangents or Gauss-Bonnet. And so then you integrate that, you use the fact that the enclosed area at time 0 is 0. And so you get an explicit formula for the area enclosed by the curve at time 2. Then you just observe that the total enclosed area has to be bounded by, at the very most by pi r squared, pi, yes. And you also notice that the total turning angle is actually increasing. And so those two facts imply that it has to go to 0 because you take t to minus infinity. The thing on the left is bounded. The integrand is monotone. So you get that the total turning angle has to go to 0, c goes minus infinity, and this gives us weak convergence to a stationary line due to convexity. And then you just bootstrap this weak convergence to smooth convergence. So that's not too hard to prove, but it's a crucial step. The next step, okay, so, modulo a rotation, we can just arrange that the limit bisector is just the horizontal one. And so we next prove that the solution is reflection symmetric about the y-axis. And that's not too hard, so let me give the picture. So in order to prove that, you just take a line through the origin, which has small but positive angle with the y-axis. Then you can always find, due to the backwards convergence, there must be some super early time at which, when you reflect the right half of the curve across this tilted line, the reflection lies above the left half of the curve. So that's more or less given to you by the backwards asymptotics. Alexandrov reflection in the parabolic setting tells you that that property is preserved forwards in time. Now you just, so that means that, this property will be true for any tilted line. You can take the angles to 0, tells you that the curve is reflection symmetric for all t. Okay, so that's not too hard, nice little argument. So we've got that our curve converges backwards in time to the horizontal bisector. It's reflection symmetric across the y-axis, so at t equals 0, it has to converge to the I want to call it the north pole, but the point on the y-axis, E2. Okay, so the final, almost the final step, pretty much the final step is to get some unique asymptotics for the solution, and that then uniqueness will follow quite easily. So the first lemma we need is this sort of Harnack type inequality for the height function. So if you think of y, say, as a function of x, think of it graphically, then at each time t, you have this Harnack type estimate for the height. And this actually turns out to be, I won't give the proof, but it's fairly easy to prove using the boundary condition and barrier arguments using free boundary circles. So you can sort of control the curvature, which allows you to control the height because the speed is the curvature and things like this. So this turns out, obviously this kind of estimate is going to be very useful. How do we exploit that? Well, we first get something on the constructed solution. So remember I said using these Ungenannt oval initial data was going to be useful. Well, we can use that in conjunction with the maximum principle to get a hold of something on our particular solution. So what we get a hold of is this minimum of the height, and we actually get that after scaling by e to the minus lambda squared t, where lambda is this factor. The lowest value of the height actually converges to a limit, which is going to be very important. So this actually converges to a limit. So this takes a little bit of work. It's not too bad though. On the particular solution that we've constructed. Okay, but now we can use this lemma, this sort of Harnack type inequality, and the avoidance principle. So the avoidance principle says that two solutions to the flow which are initially disjoint remain disjoint. The contrapositive is that if they intersect at some time, they have to intersect at all early times. Since our two solutions by hypothesis reach not the origin, they reach the point, the sort of E2 direction, 0, 1. They reach the same point at time 0. They must intersect for all negative times. Now you just apply this limit on the particular solution and this estimate on any solution to get a bound for this on any solution. Okay, we've got some control over something. Now we can exploit this. So the next step is, well, we can now prove this unique asymptotics result. That's wrong. What's wrong here? So that should be e to the minus lambda squared t. So y is going to 0 as t goes to minus infinity. E to the minus lambda squared t is blowing up when you take the product as a limit. So sorry about that. It should be e to the minus lambda squared t. How do we prove this? Sort of fairly straightforward argument. So what we do is we consider the rescaled height function. We fix any negative time tau, and we time translate our solution. So we consider the time translated flow given by translating by the factor tau. And on this time translated solution, we rescale the height function. We just consider the function defined by rescaling the height function by e to the, should probably be minus lambda squared tau. Yeah, so it should be a minus sign there. So always have this problem dealing with negative time. Anyway, and what you can easily observe is that this height function, it satisfies the heat equation. So coordinate functions satisfy the heat equation under mean curvature flow. And it satisfies this nice boundary condition as well. So that just comes from the free boundary condition. So that's quite nice. Since we know that our translated flow, as tau goes to minus infinity, this just converges, the flow will converge, in the smooth topology to the stationary bisector. So the flow, as we take tau to minus infinity, converges to just this fixed flow. And we had this estimate on the previous slide, which it implies a uniform bound for this rescaled height function on backwards infinite, on suitably bounded time intervals bounded forwards in time. And then we can apply Alaoglu's theorem to get a limit in the weak star sense. Okay, so we just need a bound for these functions, then we can get a sort of along some sequence of times, we get convergence in the weak star topology to something which is in this space. But the weak star convergence is exactly what you need to deduce that the limit satisfies the corresponding equation. Okay, you just integrate, you just use the weak notion of weak solution for this equation. And so they'll satisfy the heat equation on the limit flow, but the limit flow is just the stationary segment. So you get this nice, very simple problem. You can write down exactly what the solutions in terms of Fourier series have to be. You find out that the only unstable mode is this guy, and the corresponding eigenvalue is this one. And so all of the positive, because this solution is going to be bounded on backwards infinite closed time intervals, you can throw away all of the positive modes, and so you know exactly what it has to be. And then you more or less immediately then can deduce this. And then why is that enough? Well, now uniqueness is very easy. Once you have this unique asymptotics, uniqueness is just an almost immediate consequence of the avoidance principle. Okay, so you take your solution you've constructed, you take some second solution, and now, well, you can, up to a rotation, you can assume that they contract to the same point as t goes to 0. Now you take some small tau greater than 0, and you time translate your second solution by a small amount. Okay, by these unique asymptotics, you deduce that on this slightly time translated solution, your rescaled height function converges like this. Well, since this is slightly larger than A, then this curve, actually this time translated curve, lies slightly above your fixed solution at sufficiently negative times, but this is impossible. Well, sorry, you then take tau to 0. So that's okay. Okay, two different steps, doesn't matter which order, but the avoidance principle then ensures that it lies above for all t. You then take tau to 0, and you find that the second solution lies nowhere below your fixed solution for all t, but they both intersect at time 0. So strong maximum principle implies that they have to coincide. So fairly simple argument from avoidance once you have this very explicit asymptotics. And that's it. So that's pretty much the whole proof. Fairly nice little toy problem, and hopefully there'll be more to come in this direction.
All right, thanks, Matt. It's very interesting. I'll give you a clap emoji too.
Thank you.
You're very welcome. All right, we've got questions for Matt. We've got a bit of time.
I've got a question. What happens if you're just in a convex supporting domain instead of the disk.
instead of the disk.
You can still deduce a lot of the things you talked
Yeah,
about.
if you replace, yes, we do. We'd use a lot the nice boundary condition coming from the disk and, you know, reflection symmetry and things like that. We do use that a lot, but a lot of it can probably be replaced by more robust arguments. And I suspect, we talked a little bit about this last week with Julie and Valentina, actually. And we suspect that, you know, whenever you have so for starters, you need to have a limit bisector, and every convex body, I think by continuity, will have at least one.
Sure. The maximum width. Yeah.
Yeah, that's right. Yeah. And so there should exist a unique, you know, the backwards asymptotics part is the same thing. You'll get exactly the same equation, exactly the same backwards asymptotics.
Can you produce an ancient solution going back to any such chord just by a kind of linearization, or like a stable manifold theorem, or
no?
Manifold theorem?
You may be able to do something like that, but we're able to do it just totally directly here, because we directly get some control over the correct rescaling of the height over the backwards limit, and then you can just take a limit, and then what you get just naturally satisfies, since you know that the flow is converging to this thing, what you get just naturally satisfies this very simple Robin heat equation. And so presumably the same thing would be true. I don't know how to cook up barriers to do everything we do yet. Circular barriers, maybe you can still cook something up. Yeah.
Sounds very reasonable.
Yeah.
Yeah, I think I remember Valentina mentioning some stuff to me. She was like, "Oh, I'm doing this stuff with Matt." I'm like, sounds good. Any other questions? I don't know. I'll ask you a question, Matt. I hear what you're saying about no rotational solitons, but I just had this, I don't know, picture in my mind for ages now about filling out the whole disk by sort of yin yang curves that just get thicker and like more and more dense as you go negative time, and you could, you know, fill up the whole disk with it. Did you think about proving the existence of that kind of thing?
My guess would be an ancient solution which kind of looks like that will exist and converge forwards in time at time plus infinity to a bisector.
To the chord, right? Yeah, that's what I had in mind, but I've never really tried to prove it.
You can't get a rotating solution, essentially, because that's an ODE problem. So they have to be restrictions of planar ones, and then you can sort of, well, you can argue that none of them will satisfy the free boundary condition. You can just think of it as by checking by hand the list that's classified on the plane, and then. But yeah, I do suspect that there will be something that winds up tighter, like an ancient solution that winds up very tight, maybe foliates the whole disk.
Yeah, that's what I was kind of hoping.
I've been working for like 2 years, more than that, many years, with many people on producing something on the two sphere, which we thought would be very easy, but something that as t goes to minus infinity just sort of winds up and then has infinite.
The rattlesnake thing.
Yeah, the rattlesnake thing. That's still.
Yeah, we talked about that.
Yeah,
a couple of years ago.
That's right. Yeah, you're one of the many people who I discussed this with.
Yeah, but this seems that might be easier than that rattlesnake thing.
Yeah, it could well be.
Yeah.
A planar thing might even be easier. Maybe the free boundary is easier, but the same question can be asked in the plane as well.
Yeah, cool. Any other questions for Matt? Okay, if not, let's thank him again.
Thank you all.
Looking forward to the higher dimensional results. I mean, I guess you can't just rotate it, right? You can't just rotate it like this or like that, you know, get catenoids or Clifford tori, but something like that maybe.
Yeah, no, you definitely can't get it just from rotating, but you can do similar stuff.
I guess it's harder.